Welcome to another Team Talk episode, this time featured at the space of the Research Institute for Arts and Technology.
Superb.
Okay, next up we have some people requested or expressed that they would like to have more technical insight, more technical details, more in-depth view on the developments, the small things changing here and there, electronics, hardware, software. You're going
to explain it now to us?
I'll explain some of the small changes. Maybe you will also want to explain one or two small changes.
Techno vampires should try this at some point. And
we are the new generation of tech vampires here. Okay, the new change is on the back of the Beta. We have a small fan, and at first this fan was attached with a threaded rod and just nuts from two sides, below the microset and on top of the fan. Then in between we found matching metal screws that kind of have exactly the right dimensions, so you don't need nuts anymore on both sides. And now we have the newest iteration is that we have nylon screws. They are lighter, they make the fan more silent because there are no kind of metal parts touching each other. And yeah, they look similar to metal because they're black, but it's actually plastic. Also related to the fan is that we in the beginning had attached the power supply of the fan on the microset itself.
Yeah.
And the control was limited, and therefore we moved that connection to the main board where we have a dedicated header now and can control the fan speed from software. In terms of the PCB stack, in the beginning we had just the threaded rods and nuts holding everything in place, and the distances you had to kind of manually adjust and check that the boards are not too densely screwed to each other. And now we have a solution with exactly
It's nylon.
It's nylon. There are nylon spacers that have exactly the same dimensions as the connectors stack up between the boards. So now there's much less mechanical stress from one board pushing the other board. And in the beginning we had on the power board the FTDI chip, a USB connector. We had problems with power feedback. Yeah. And
the middle one is the power board.
Yes, and there's a small USB connector here, and there's a small chip next to it, FTDI. And as we said, there are problems with power feedback in the beginning. Then we started using I2C bus for testing and debugging. And
I thought they said no more teleprompter.
That's why I'm so bad at reading. It doesn't make sense. And now we changed the power board schematics to kind of prevent that kind of power feedback altogether.
All right.
So it actually was a hardware upgrade.
What changes now for the people who already received the old version of the power board?
They can get a new version of the board, or maybe they don't even have the issue of using the FTDI chip if they're not developers. Maybe it's not that big of a deal.
All right.
On the power board, we had trouble with the I2C connection. It's a communication bus to the main board, and we replaced the connection component, the small chip that now has a reset, and that way it's fixed. It's also a hardware change. In the beginning, on the main board, we had flash memory for development. And this is replaced now because it was rather slow, the connection was slow, you could only program it slowly, and we placed a PIC microchip controller underneath the lattice FPGA, and you can now program everything much faster because there's a dedicated kind of chip for that, for routing, data routing, flashing.
That makes sense, yeah.
We already mentioned the fan control on the main board for the fan on the microset, and there's a small buzzer as well that the Beta can actually make noises a little bit, if required.
Which noises?
I don't know, like everything your Game Boy can do. It's a buzzer speaker, so it's not like a large speaker in that sense.
Cannot curse at you for bad exposure.
Maybe that's a very important upgrade for the future.
I agree.
Is that mildly amusing?
No,
Oh,
it's not.
okay.
Not
You caught me off guard. So.
Okay. We'll try better. We'll
Yeah,
try better.
we'll try better cutting it out.
So today I want to show you how you can actually run the camera through the fixed pattern noise calibration procedure. The essential thing we need here is a so-called dark frame. It means that you collect the data from the sensor when the camera is actually not receiving any light or any photons are hitting the sensor. So for that purpose we actually have to make sure that there is no light getting anywhere near the sensor. So you attach the lens cap that I don't have right here. I will also attach a kind of lens bag to the lens. You can close down the iris as well, just in case. Now we are on the command line interface of the camera, and we run a command on the PC connected to the camera, and we capture 64 frames exposed all at the same exposure time of 12 milliseconds, and just let this run through a script from the camera. This will take a bit of time. With this set of 64 frames, we now run them through a tool, raw to DNG, with a certain set of parameters for calculating a dark frame. This also takes a bit of time, and with the resulting file called in this case dark frame rcn.pgm, which we transfer to our beta now. What we actually do now to make the effect of the change more visible is that we use the 4x4 matrix to intensify and exaggerate the image on the camera. We actually load this file with a script called RCN darkframe, a Python script, and it takes the darkframe as parameter and is done afterwards. After calibration is done, I turn the matrix back to normal, take the camera out of its bag again, open up the iris, and the image the camera creates should be much cleaner without any fixed pattern noise left.